The momentum of a body is defined as the product of its mass m and velocity v. Momentum is denoted by P. Since mass m is a scalar and velocity v is a vector, their product, momentum p, is a vector. In the SI system, momentum is measured in kilogram meter per second or Newton second. Force, momentum and time are interrelated. Let us check some scenarios to illustrate this. A boy standing in a first-floor balcony drops a ball of mass m from a certain height h. As the ball goes down, it gains some velocity and hence acquires a certain momentum. A boy standing on the ground below catches the ball by using a force F. The momentum of the ball becomes zero during the process of catching it, as it comes to rest. Another ball of mass 2m is dropped from the same height. This time, the force required to catch the ball is 2F. Between these two scenarios, the mass of the ball doubles, but the final velocity remains the same. Therefore, the momentum of the ball also doubles. Consequently, the force applied to catch the ball also doubles. Here, the momentum of the ball increases due to an increase in its mass. In the same scenario, if a ball of mass m is dropped from the second-floor balcony from a height 2h, its velocity increases and therefore its momentum also increases. Consequently, more force is required to catch the ball. Here, the momentum increases due to an increase in velocity. In all these three scenarios, the ball has some momentum when it touches the hands of the boy catching it. However, the momentum becomes zero as the ball comes to rest due to the force applied by the hands for some time. The force required to stop the ball and the length of time the force is applied are related to each other. A wicket keeper, after gathering the ball away from his body, pulls his hands towards himself to avoid injury to his hands. This proves that less force is required when it takes more time for the ball to come to rest. Now, let us look at another example, where the body is at rest initially. That is, it has zero momentum, and by the application of a force for a certain time, it acquires some momentum. A small car is at rest. 4 persons push the car for a certain length of time, at the end of which the car moves with a certain velocity. We say that the car has acquired momentum. A truck is at rest. The same 4 persons push the truck for the same length of time, at the end of which the truck moves with a velocity lesser than that of the car. However, the momentum acquired by the truck is the same as that acquired by the car. In these two activities, the force applied and the length of time for which the force is applied are the same. Therefore, the momentum acquired is also the same even though the mass of the car and the truck is different. Hence, a body of lesser mass moves with greater velocity compared to a body of greater mass, but the product of the mass and its velocity remains the same in both cases. In these examples, there was a change in momentum due to a change in magnitude of the velocity of the body. There was no change in the direction of motion of the body. What happens when the magnitude of the velocity of the body remains the same and only its direction of motion changes? Since the velocity vector changes direction continuously, the momentum vector also changes direction continuously, and this change requires some force. Consider a sling being whirled such that the stone and the thread rotate in a horizontal plane with uniform angular velocity. The magnitude of the linear velocity of the stone remains constant, but its direction changes continuously. To sustain this kind of motion, we have to continuously apply a pulling force on the thread. From these examples, we have understood that a force has to be applied on a body for some length of time, during which a change in momentum is taking place. In other words, the momentum of an object increases when it accelerates and vice versa. Therefore, the rate of change of momentum depends on the acceleration of the object. Newton's second law of motion brings out this relationship between momentum, acceleration, and force. Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Consider a force F being applied on a body of mass m for a time interval of delta t seconds. This results in change of velocity of the body from initial velocity v to final velocity v plus delta v. Here, initial momentum p is the product of mass m and initial velocity v, and final momentum p plus delta p is equal to the product of m final velocity v plus delta v. On simplification, we get the change in momentum of the body, delta p, as the product of mass m and the change in velocity, delta v. According to Newton's second law of motion, force is proportional to the rate of change of momentum. Bringing in the constant of proportionality k, the equation becomes F equals k multiplied by delta p by delta t. When delta t tends to 0, delta p by delta t equals dp divided by dt. This makes the above equation F is equal to k multiplied by dp divided by dt. Substituting p equals mv in dp by dt, we get dp by dt is equal to mdv by dt, or ma, since acceleration a is the rate of change of velocity v. Therefore, F is equal to kma, defines Newton's second law of motion. By choosing the values of k as 1, we can define the unit of force in the SI system. In the SI system, the unit force is one that causes an acceleration of 1 meter per second square to a mass of 1 kilogram. This unit force is known as a Newton. There are certain special applications of Newton's second law of motion. When no force is applied on a body, there is no acceleration in its motion, since the mass of the body cannot be equal to zero. This is one way to write Newton's second law of motion. Since force applied and momentum are vectors, we can apply the law by taking their components in the three coordinate directions, that is, x, y and z. Fx is equal to dpx by dt, which is equal to max. Fy is equal to dpy by dt, which is equal to may. Fz is equal to dpz by dt, which is equal to maz. F here stands for external force acting on the body. When a number of forces are acting on a body, we should take the net force in the equation as sigma F is equal to ma. Newton's second law applies to instantaneous force and instantaneous acceleration. Newton's second law of motion can also be written as change in momentum is equal to the product of force applied and the length of time for which it is applied. If a very large force is applied for a very short duration of time, it results in a large change in momentum of the body. This large amount of force acting on an object for a very short duration of time is called as an impulsive force or impulse. Measuring this force and time is difficult. However, the change in momentum can be measured, which is equal to the product of force and time. A bowler in a cricket match bowls a full toss ball and the batsman hits a six. In this example, the batsman has applied an impulsive force on the ball, due to which there is a tremendous change in the momentum of the ball.